Jai students, welcome to my YouTube channel. Students, the beautiful thing about learning is that no one can take it away from you. That is, when we keep learning, it helps us to gain new knowledge, develop skills, and have new experiences along the way. It enables us to keep our brains active and engaged. The capacity to learn is a gift. The ability to learn is a skill, and the willingness to learn is a choice. Students, in this particular session, we are going to discuss Faraday's experiment, and in the process, we'll also discuss the laws of electromagnetic induction. Let us familiarize ourselves with the setup which we'll be using. This is a setup which can be used to verify the laws of electromagnetic induction. And in this setup, first and foremost, we will discuss about the battery eliminator. A battery eliminator, as the name suggests, it eliminates the need of batteries to power a circuit. A battery eliminator actually converts the source to a suitable DC voltage, and it can be used to provide a variable voltage between 0 to 12 volt. This is the on-off button. By switching on the AC current, the AC input current, that can be converted into a desired DC output voltage. Now, these are the slots 2 volt, 4, 6, 8, 10, 12. As I have stated, it can be used to provide variable voltage between 0 to 12 volt DC. Now, students, this is a very important and interesting apparatus which is ideal for the magnetic field and induction experiments. This is to demonstrate that the induced potential is generated either by the movement of a permanent magnet or an electromagnet, or by charging the current in a single coil. Now it consists of a strong and high quality pair of coils. These are the two coils. The small coil has about 400 turns of heavy wire and fits inside the larger coil of 1200 turns of fine wires. And this is a removable iron core. This iron core fits inside this smaller coil to make the complete set. The sizes are arranged such that the set of three items hold together when lifted as a set. These are the terminals of the large coil. A galvanometer is to be connected between these two terminals. So students, this entire setup, which is known as the mutual induction apparatus, is a high quality instrument which is designed to demonstrate the fundamentals of magnetic induction. Now as you can see, these two ends of the large coil are connected to the terminals across which a galvanometer is to be connected. The two connectors from the battery eliminator needs to be connected to these two terminals of the smaller coil. The unit is complete with a primary coil containing few turns of large diameter copper wire and a secondary coil which fits over the primary coil. The secondary coil contains many turns of small diameter copper wire, and this is a soft iron core which passes through the center of both the coils. On placing the metal core inside the coil, the magnetic lines of flux is concentrated on the core, which eventually increases the induction of the coil as compared to the air core. Now students, this is a sensitive galvanometer, and it is a device which is used to detect the current. So when the current is produced in the secondary coil, then the needle in the galvanometer will give deflection. As I've stated students, the galvanometer is to be connected across the terminals of the secondary coil. It is actually a long piece of wire which is wound in the shape of a coil. When the electric current passes through the coil, it creates a relatively uniform magnetic field inside the coil. Now let us understand the procedure so as to use this setup to experimentally verify the laws of electromagnetic induction. As told earlier, the inner coil is the primary coil, while the outer large coil, that's the secondary coil. Input is always fed across the primary coil, while the transformed output is obtained across the secondary coil. These are the terminals of the inner primary coil, and it is to be connected across the input source, which is the battery eliminator. And these are the terminals of the secondary coil, and it is to be connected across the galvanometer. And initially, the galvanometer is showing zero deflection. Now, as the power of the battery eliminator is switched on, and let us give it a voltage of 2 volt DC to the primary coil. Now students, as the inner coil is moved in and out of the secondary coil, then due to the relative motion you can see the galvanometer gives some deflection. Now let us repeat the same experiment for higher voltage, say 4 volt. In this case also we will find that when the primary coil is moved towards the secondary coil, then the galvanometer will show deflection. And in case the primary coil is moved away from the secondary coil, then the galvanometer again shows deflection but in the opposite direction. One more thing students, the faster the relative motion, the more appreciable the deflection in the galvanometer. So the EMF or the current induced in the secondary coil must be proportional to the time rate change in the magnetic field or the magnetic flux. The faster the relative motion, the more is the deflection observed in the galvanometer. And now students, as you can observe, the slower the relative motion, the lesser is the deflection in the galvanometer. So, the EMF induced in the secondary coil does depend upon the time rate change in the magnetic flux. Students, the same effects will be observed if the current carrying primary coil is replaced by a bar magnet. So basically, the induced EMF or the induced current that is produced in the secondary coil lasts as long as the change in the magnetic flux or the magnetic field continues. Now students, in the absence of relative motion, as you can see, when both the coils are held stationary, then the galvanometer is showing zero deflection. That is, no EMF or current is induced across the secondary coil. This phenomena of production of an induced current in the secondary coil whenever there's a change in the magnetic flux linked with the coil is known as electromagnetic induction. So students, these are the observations and the conclusions which I have written in a tabular form. So the whole experiment, or rather the whole activity, suggests that whenever there's a relative motion between the coil and the source of the magnetic field, then an induced voltage or current is produced in the coil. Now, when I say source of magnetic field, it can either be a bar magnet or a current carrying coil. In our case, we have considered a current carrying coil, which is the primary coil, right? So due to relative motion, what happens is the magnetic field or the magnetic flux linked with the coil changes. So students, we can conclude that whenever there's a change in the magnetic flux linked with the coil, an EMF or a current is induced in it. So that's first law. And students, we've also verified that this induced current or EMF or voltage lasts in the coil as long as the magnetic flux linked with the coil keeps on changing. So when the two coils are held stationary, then no change in the magnetic field or flux takes place, and accordingly the galvanometer shows zero deflection, which indicates that no current is induced in the coil. And students, last but not the least, what we have concluded is that the faster the relative motion between the two coils, the large is the deflection produced in the galvanometer, which clearly suggests that the current induced in the coil is directly proportional to the time rate change in the magnetic flux. The faster the relative motion, more is the magnitude of the voltage so produced in the coil, and vice versa. So these conclusions are collectively known as Faraday's laws of electromagnetic induction. Here I would also like to mention that the voltage or the current so induced in the coil is always of opposing nature. It always opposes the changes or the causes that produces it, right? So that's it for this particular session, students. I hope you have thoroughly enjoyed this session, and do keep watching my videos. Thank you.